me in here. And yeah, why don't we get started here? So welcome everybody to our spring semester, our second semester of the Science by Diverse Scientists Calibrate Physics and Astronomy seminar series. We had a nice series of talks in the fall, all of which you can find on the Calibrate YouTube channel if you go to the webpage for this series here. Here's a preview of what our lineup is for this semester. So we've got another 5 talks lined up here. It's a few spots to fill in still at our TBA, so you can see what our plans are for the rest of the semester here. And also say this, right? So this series is a project of the CalRIDGE program for just connecting Cal State students to graduate programs at the University of California, and our seminar series is sponsored by the Research Corporation for Science Advancement. This is organized by a committee that includes me and Sarah Kalori that's here, and also Carol Hood, Alex Miller, and Aaron Romanowski. And we have also here as a panelist, Alex Rudolph, the director of CalRIDGE. Okay, so looking specifically to our talk today, we're pleased to have Dr. Ronnie Shepard from Lawrence Livermore National Lab. He's going to give us a talk entitled Utilizing Short Pulse Lasers to Explore Matter at Stellar Conditions. To tell you a little bit about Ronnie, he received a bachelor's, master's, and PhD from the University of Michigan, all in the Department of Nuclear Engineering and Radiological Sciences, which was in 81, 83, and 87. Currently at Lawrence Livermore, he is an experimental physicist in the Physical and Life Sciences Division, and he's also the Director of University Outreach and Collaborations at the High Energy Density Sciences Center at Lawrence Livermore, in which capacity he's also part of our collaboration that I'm part of with UC Merced with Lawrence Livermore about training students from minority serving institutions in high energy density science. Ronnie has been at Lawrence Livermore for the past 33 years, and he has performed research there in areas related to X-ray lasers, shock heated matter, and all kind of different laser systems, which he's going to be telling us about today. So thank you very much for joining us today, Ronnie, and the floor is yours. Oh, and sorry, let me just also mention before we get started, feel free to ask any questions in the chat as we go. We'll answer these at the end. Yeah, in the Q&A, you can write in your questions, and then we'll moderate them. And also students are invited to stay on at the end for an informal chat with Ronnie. Okay, floor is yours.
All right, thank you. Thank you, David, for that gracious introduction. Okay, so I share my screen now. I guess it's here.
Absolutely.
And I say, okay. So yeah, I am Ronnie Shepard, and as David said, I've been at Livermore for 33 years, and I had I would say an interesting path to get there, and I can discuss that with students afterwards. I'm going to tell you about a field which sort of grew out of the development of these short pulse lasers, but the idea is to try and understand how stellar interiors work using short pulse lasers. And the way that's done is using short pulse lasers to create these unique high energy density states of matter. And feel free to, I guess you'll have to ask the questions in the chat, but feel free to ask questions. There are no questions that are too simple or well, there are questions that are too complex, but there are no questions that will be too simple. I'd like to begin by giving you some idea of why we are interested in doing this, pursuing this area of studying matter at these extreme conditions. And that'll be early in the presentation. Some of these things will be a little simplistic for some of you, and some of these things may be a little, you may consider to be a little complicated. And I implore those that feel as if some of this stuff is a little too slow for you, just be patient. But I'd like to make sure everyone gets something out of this. So after explaining to you why we are interested in studying this matter under these conditions, I'd like to then give you some idea of how we do this using short pulse lasers and what we actually try to measure. And some of those quantities are opacity, which is a key component to understanding how stars evolve, a physical process that happens to atoms called continuum lowering, electron ion of collaboration, which is just understanding how fast particles come into equilibrium with one another. And the last thing I hopefully will tell you about, there is one other thing, thermal conductivity. Hopefully there'll be time for that. And the final thing is a sort of a new endeavor that we're trying, which is to try to test this basic principle of physics called Einstein's equivalence principle. And that's kind of an idea that's in development. So you're going to know as much about that idea in development as I do when I explain it to you. So to start with, why are we pursuing this? Well, let's see. I don't think we want that. Okay, there. Yeah. So to start with, if you look at a star and peel it open to see what's inside of it, what you'll find is that at the core of the star is sort of a nuclear furnace. That's where the energy is being generated, called the stellar core. That's done by fusion reactions, taking small particles, pushing them together, getting them to stick together. And when that happens, you release a large amount of energy. That energy is then transported out to the outer rims of the star through what is called a radiative zone. That's where the processes are dominated by radiation, which is basically light. And then a convection zone, which is the process of moving energy around by physically moving matter. If you were to try to explain how the temperature varies inside of a star, you could write down some fairly simplistic equations. Now, try not to be too enamored or too scared off by these equations. The equations are just to illustrate that you can write down something that gives you a dependence of the temperature on the physical quantities of the star itself. And that's a function of this R is the radius of the star. So these quantities that you see here, there are physical quantities. There's a quantity you can see, I circled it. Has a kappa. That's the opacity. That shows you that the temperature of the star is dependent upon this physical quantity called opacity. You can see there's another quantity that's this mu. That's the thermal conductivity. There's a third quantity here, which is this gamma, which is really a fundamental property of the equation of state of the material. We don't actually try to make that measurement, but there are people at the lab that do make those measurements to try to understand that parameter as well. And they've had a lot of success at that. We're trying to measure these other parameters, this mu, this kappa, and in the process of doing that, try to understand some other fundamental physical properties like how long it takes energy to exchange between particles when the temperature changes, which is the electron ion of collaboration. So that's kind of the reason why we want to do that, though, is because the entire cooling process of the star is really dominated by those simple quantities, the thermal conductivity and the opacity. That's how the energy gets rid of it. That's how the star gets rid of its energy. So if you look at how a star is born, you start with a cloud of dust and mostly hydrogen. And the gravitational pull of that mass collapses. And as it collapses, depending upon where it started, you can either form something like a small star, which it's called an M-class star. That star will evolve, eventually burning its nuclear fuel. And as it burns its nuclear fuel, eventually it starts to expand because the radiation, the pressure from the inside the star will overcome the gravitational pull as the fuel burns out. Eventually it expands, and because its initial mass actually dictates where it dies, that expansion portion forms a planetary nebula and eventually forms something called a white dwarf. Actually, most stars in the universe will die like that, will eventually form white dwarfs. If the initial stellar cloud is big, then it forms a large star. It goes through the same evolutionary process, burning its nuclear fuel, converting hydrogen to helium, helium to lithium, and so forth. But eventually, when it reaches some point where it can't burn any more of its nuclear fuel for various reasons. The particles can't overcome the repulsion. At some point, it expands to the point where the gravitational pull, it just rapidly collapses. The radiation pressure is not adequate to sustain the gravitational pull. It rapidly collapses and it produces a supernova. And the byproduct of that is, one thing is that it makes all these metals, high energy, high Z metals, gold, platinum, so forth in the periodic table. But the byproduct is a neutron star or a black hole. The bottom line, though, is that entire process is really dependent upon the parameters that we talked about on the previous view graph. How long does it take for the star to radiate its energy away? That's really what's dictating how long this process takes. And by learning and understanding how that process works, you can really get an idea of how long all the stars will eventually, how long they will last, and how they will die, and how the universe will go away. So that's kind of a far-reaching motivation for trying to understand these very simplistic parameters that dictate how stars evolve. Okay, so now I'm going to explain something that's pretty, that's kind of going to be simple for some people, but I thought it's necessary to do this because much of what we're going to be talking about is based on understanding the state of matter that we're studying. So if you look at matter, we're all familiar with a solid. We're all familiar with, if you put energy into a solid, you form a liquid. You put more energy into a liquid, you form a gas. But if you continually put more energy in, the gas particles begin to break up into atoms. And the atoms then form a sort of fluid material called a plasma. And that plasma is really just a collection of positive and negatively charged particles. And it is one of the most common forms of matter in the universe. I mean, it's what's inside of stars. That's what stellar interiors are made of, is plasma. By trying to control those reactions that occur inside of a star, you can generate energy. That's one of the big programs at Livermore, is trying to make a sustained source of energy called thermonuclear fusion. And that's done by actually taking hydrogen or water and converting it into energy. And the final thing is, when those nuclear reactions are not controlled, it forms a nuclear weapon, a nuclear bomb, which is also the reason why places like Livermore are interested in understanding how plasmas work. Okay, so how does fusion work? Now, some of these things are a bit simplistic, but I thought it'd be interesting to show this. If you take what's called deuterium, which is really hydrogen with an extra neutron, and take tritium, which is hydrogen with 2 extra neutrons, and you heat those, you force them to get close enough together by heating them. When you do that, they fuse and create a helium nucleus. So you you started with essentially 2 hydrogen nuclei. You fuse those together, it forms helium, and an extra neutron goes away, and you have kinetic energy, and that energy is what is often used to, you can use it to make a power plant, or like I said, it can make a nuclear bomb, or it makes a star. But if you're, oops, okay, so yeah. So if you look at the periodic table and you wonder where those elements come from, that's where they come from. All these elements come from like, except for hydrogen, they all come from formation inside of a star. Everything that we know of has started somehow in a star. Every element in that periodic table was born in a star. So as I pointed out, one of the things Livermore does, one of the things that's done at Livermore is trying to recreate the process that occurs inside a star using very big lasers. Now, this is not what we're doing with the short pulse lasers, but I thought it might be instrumental, or it might be interesting to show how places like Livermore are trying to recreate that same state of matter using big lasers. Nature does it naturally, but with gravity, but we can't do it with gravity because it turns out gravity is a really, really weak force. And it's not, you need a lot of mass to overcome the Coulomb, the repulsion of same charged particles. So how is this done? Well, this is a little movie showing the process that Livermore uses, using the world's most powerful laser, the National Ignition Facility. The way it works is an experimentalist will call for a shot using this big laser. There's a guy who runs the laser and says, okay, are you ready for the shot? And the experimentalist says, yes, please fire the shot. This is a cartoon showing you how that process works. You fire the shot, a little tiny laser pulse is then released from the room where the operator sits. That laser pulse is then amplified. So you see these things bouncing back and forth, those are amplifiers. That laser pulse gets split and amplified over and over and over and over again. So what started out was with just a little tiny little bit of light, a tiny portion of light, millijoules of light. It then gets amplified and amplified and amplified. And so here you're traveling with the laser beam, one of the laser beams, and then it propagates. Those are laser beams. It gets split into 192 beams that all get amplified. They all get amplified. Eventually, they approach the target chamber. Now they do something that's really kind of cool. They change the color of the light from red to blue, and there are reasons for doing that. That light then gets focused inside of what's called a Hall room, which was German for cavity. And that each of the beams hits the walls of the Hall room, which creates X-rays. Those X-rays then heat a small sphere which holds hydrogen gas inside of it. The walls of the sphere blow up. It creates an opposite reaction which compresses the gas, fuses the particles together. And so that's how it kind of works. I mean, that's how you can make a kind of a star on Earth. In order to understand the process for making that work, once again, you need to understand these same parameters that I was speaking of before to understand how a stellar interior works. You need to understand those same things, the opacity, the conductivity, in this case, the electron ion collaboration as well. All those things play into understanding how that process works. So in the end, what do we do? So someone comes along with a brilliant idea, says, okay, how does this process work? You start with some idea. Okay, well, the idea gets fed to some experimenters like myself. We go off and say, okay, well, Let's test and see if this idea works. Simultaneously, someone running computer simulations will then test on a computer to see if the computer can predict how the experiment will work. That gets combined with a result. That result then gets compared back to that basic theory or the equation. And then you say, well, how well did we do? And you either say, well, it looks pretty good, or you say, well, nature doesn't work that way. And then you iterate. You say, okay, we need to improve. Maybe you have to improve the experiment. Maybe the experiment didn't quite work right. Maybe the computer simulations need some more information. Or maybe the brilliant idea really needs to be iterated on. Everything worked in the experiments and the simulations, but it turns out the brilliant idea wasn't quite right. Nature doesn't work that way. So you iterate. And that's kind of the process that all of this works on. All science sort of works on that premise, is this circular sort of iteration, improvement, taking sort of small steps at a time. And I just thought I'd include that because often people say, well, okay, what do you really do? What we're really doing is doing the experiments part of this and then comparing this to both computer simulations and the basic theory that we started with. Okay, so how are we testing these things? Well, we use these short pulse lasers. And I'll explain why we decided to use short pulse lasers. But first I thought I'd explain how we make these short pulse, these really high intensity short pulse lasers. It involved a trick. This guy, Gerard Moreau and Donna Strickland, came up with this idea. People figured out how to make really, really short pulses of light. You know, it's so short that if you could see it propagating in air, it would be about the size of a pinhead. That's how short it was. I mean, it was really short. It'd be like a pinhead of light just kind of propagating through space. But the problem was that people couldn't figure out how to make the energy big and utilize it. So this guy, Gerard Moreau, came up with this idea. Well, if I can make the pulse, I can take that short pulse and make it longer and amplify it. And you would say, well, why can't you just amplify the short pulse? Well, the problem is that power sort of is inversely proportional to time duration. So the power in that short pulse is actually extremely high, even though the energy can be small, because the time duration is so short, and because power is inversely proportional to time, the power in that is really, really high. So you would say, well, so what? Well, the material that you use for amplifying laser light gets damaged. The damage is proportional to the power that's propagating through it. So because this tiny, tiny pinhead of light is propagating through this material, it instantly damages it. And so you can't amplify it. So this guy came along with this idea, well, what if I could stretch it in time, amplify it, and then shrink it back down in time? And it sounds obvious, but it turns out it's not so easy to do. He came up with the idea to do that. And the way he does it is the short pulse has a lot of colors. It's broadband. It has a wide range of frequencies in it. And by dispersing that short pulse, it spreads it out in time. And so they use a grating, which is very similar to just using prism or something, but you spread it out in time by dispersing it. And then you then amplify it after it's been stretched. You can see in the cartoon, it says stretch pulse. It goes through the amplifier. It gets to be a big pulse, but now it's long in time. And to make it short again, you do just the opposite. You then recompress it by, in this case, it has gratings, but you do just the opposite. So you take the colored light and make it like white light again. You just shrink it down. And that sort of simple process led to an entire revolution in utilizing and how lasers could be used. And it was so clever that the pair of them, Gerard Moreau on the left, Donna Strickland on the right, was his student. They won the Nobel Prize for this idea in 2018. So what did that mean for someone like me? Well, someone like me who is trying to study something like stellar interiors, the problem has been historically is that you use longer pulse lasers to start with, to hit or heat a piece of solid material. And the problem is that the duration of the heating process is sufficiently long that by the time the maximum amount of energy reaches the solid surface is no longer solid. It's expanded out. And that's because as you heat it, it expands. So the problem was that you couldn't really heat something at solid density. And I didn't explain this, but the cores inside of stars are solid density and greater. So you really want, if you really want to replicate what's inside of a star, you need it really, really high density material, but you need to get it really, really hot. So these longer pulses didn't quite work because the material started to expand it before you could deposit most of the energy. As you shorten the pulse though, what you find is that the inertia of the material is sufficiently high that the material doesn't have time to move. So if you deposit it fast enough, the material doesn't have time to move. And for some short duration of time, if you can make your measurements during that time frame, you can then study the material at extremely high densities, solid densities, and using some clever tricks, even higher than solid densities, at extremely high temperatures, at temperatures that will be comparable or even exceed what you can find inside a star. So that was the platform developed. Now we actually added some twists, a couple of twists to it to further enhance this idea of maintaining a high density. And this is a series of cartoons. Once again, ignore the equations, but you can see on the left-hand side of the screen, there's an image showing a laser, and you can see a thin layer, and then there's two translucent layers on either side of it, and that's what we call a buried layer. And that further decreases the expansion of the material of interest. So the way we do this is we put the material interest on either we put the material interest underneath two layers or layers of material that we don't really care about, but it's used to confine the expansion of the material that we care about. And we then make measurements with really, really high time resolution diagnostics to determine the characteristics of what's happened to this layer of material. And this is a calculation which was done sort of illustrating that. And this is, I'll be brief here. This axis is actually time. So this is picoseconds. That's 10 to the minus 12 seconds. And this is the dimension, the thickness of the layer. And this is hard to tell, but this is actually 2,000 angstroms. From this point to that point is 2,000 angstroms. And the color indicates the density. And this was done for aluminum. Aluminum starts at 2.7 grams per cc, which is, up here. And that's why it's red. But as the material gets heated, the laser hits the target, you can see initially it starts to expand. It starts to expand, but that's because it's being held in with plastic. And it turns out the density of the plastic is higher than the density of the plastic. The density of the layer, is higher than the density of the plastic. So it expands into the plastic initially in order to maintain hydrodynamic equilibrium. So it equilibrates with the plastic, but it does that really fast. But then after it does that, it just sort of sits there at one density. And this is roughly 1.8 grams per cc. It just sits there for about 20 picoseconds, which you may say, well, that's not very much time. And then eventually what happens is the plastic starts to expand and it eats into eventually catches up to the heated layer. And then the whole thing starts to expand. But until this 20 picoseconds of time, we have that much time to actually study this plasma, which it turns out, when we made the measurements, it was at temperatures that were comparable to the center of the sun, but at solid density. So it immediately said, well, this is a platform we can use to really study plasmas in the conditions that are in stellar interiors. Okay, so what things do we try to study? I said radiation transport is the big one. And that's because most of the energy is lost in a star by the escaping radiation, which is what we see when we look at stars. Thermal conductivity and electrical conductivity is a big one because that is how energy is transported via collisions. The electron ion relaxation is more an issue associated when you have rapid changes in temperature in a star, which is not very often, but occasionally you have these rapid changes in temperature. Usually it's from expanding gases. And the question is, how long does it take for that energy to get transferred between particles as you expand the gas? And then there are other issues. Now, I'm not going to talk about all of these things. I'm going to try to talk about just maybe 3 of these things, and then I'm going to try and move on to this new idea that we've been thinking of doing. So what is opacity? Gee, I don't, are you guys, is this stuff at the top a problem? I don't know.
Looks fine
so
to me.
Anyway, first, how do you measure opacities? Normally what you do is you have what is opacity? So opacity is the attenuation of light, that is how much light gets through something. So for instance, if you have sunglasses and you put your sunglasses on, you're looking at the sun, which you probably shouldn't do, but you look at the sun, the opacity is the quantity of light that gets attenuated by your sunglasses, or how that light gets attenuated by your sunglasses. So there's some light that starts on the other side of your glasses, and there's some light that gets through to your eyeball. And the opacity is kind of the ratio of those two things. So an expression for that, this is kind of a cartoon showing opacity. So you have to start out with something bright on one side, and you have something that attenuates, that decreases the brightness of that light, and then you have your eyeball or something on the other side. And so there's this thing called Beer's law, which is a mathematical expression which describes how that light gets attenuated, how it decreases. But it's dependent upon this thing here, this kappa, which is in a smaller or reduced form is really the density of the material times a fundamental property of the material itself, which is the opacity. Okay, but if you really wanted to make measurements about this, you really need 2 things. You need a bright source, and you need an eyeball, and you need to know the density. But you really want all this at one density and one temperature, which is difficult to do if you have you're doing this with a long laser pulse, because you do it a long laser pulse, as I pointed out before, it heats and it starts to expand. So you don't get one density and one temperature. So you can't really make that measurement like that. It's a really difficult way to make the measurement. There's an additional problem, and that's that as this thing that you're looking at gets hotter and hotter, this thing that's backlighting it, this thing that you're trying to get through it, has to get brighter and brighter. And that leads you down a death spiral. You can't eventually make this thing bright enough in order to see it through the thing that you're trying to measure the opacity for. And that's because this thing is brighter than that. It's closer to your eyeball than this. So there's some fundamental problems trying to make these measurements on something that is not like sunglasses, but more like something like the sun, something that's really hot and dense. So there's this trick you can use, though. It turns out if you, once again, ignore these equations, there's this trick you can use that is a fundamental property of hot matter. And that's that if the matter is really hot and really dense, and the processes that lead to the emission reach an equilibrium state, that is, the things that are being emitted are as quick, they're being as emitted or as quickly absorbed, then it reaches an equilibrium state. And then whatever you measure coming out is exactly the same as what would be absorbed inside the material itself. And that's called Kirchhoff's law. And that's the premise we use with these short pulse experiments. We don't actually measure the emission, the absorption, we actually measure the emission. And we know, because we know the conditions of the material, that if we take that structure, which looks like emission, and simply turn it upside down, that's exactly what the absorption looks like. And that's a powerful tool. That's a very powerful thing, because it allows you now to make measurements at conditions that normally you could not make. You simply could not make, because you can't make a bright enough backlight or a bright enough source to get through the hot material. And it's hard to actually get the material hot and not expand. So it's a very powerful tool that we use, and that's how we make the opacity measurements. Okay, I'm going to skip over this. This is the primary facility we make these measurements at currently is a facility in England called Orion, but I'm not gonna dwell on that. I'm going to move on to what's called ionization potential depression, which is an effect that happens to bound electrons as density goes up and up and up. Those outermost bound electrons get confused, or we're confused as to what they really do. And you say, well, how does this affect a star? Well, the highest stars are mostly hydrogen and helium, but the opacities are really dominated by the small amounts of high Z material that's in the star. It's called a metallicity. Well, one thing that confuses us is how many bound states remain as the density of the star or the density of the matter goes up. And this is a cartoon showing what happens in various states of matter. When the matter is kind of a hot plasma, what's called the free states, which are up here, are well separated from the bound states. And we know how to explain that. And the equation of state for the material is really a form of the ideal gas. If you go to the opposite extreme, cold material, the bound states overlap with these free states and form continuum states, which then form something called band structure. And because that's not dynamic, for the most part it's not dynamic, we actually have a very good understanding of that. Solid state physics does a very good job of explaining that. The problem is here in the middle, is when you have these continuum states that overlap with the bound states in sort of an unpredictable way. And then you have something that's called pressure ionization, and we don't really know where the bound states stop and the free states begin. And you say, well, what does that matter? Well, it matters because those bound states are what's dictating the opacity of the material. So we struggle with understanding that very basic fundamental physics. And okay, well, this is sort of a cartoon illustrating that for particular material, potassium. On the x-axis is density, and on this y-axis is bound electrons. And potassium has 19 bound electrons. And as you can see, if you don't change the temperature and you just slowly increase the density, what eventually happens is the number of bound electrons decrease, right? And what's happening is the surrounding positive charges are beginning to overlap with those outer bound electrons, but it's doing it sort of in an unpredictable way. It's what we often say is that the wave functions for those electrons, that's a sort of complicated thing, but what it says is they're becoming delocalized. That what it means is those electrons are starting to be shared with other atoms, but we don't quite understand how it's doing it. And as you can see, as you continue to raise the density, more and more of these electrons, there's fewer and fewer bound electrons. And these are just theories. And you can see the theories are all disagreeing. They don't really know. One theory is saying there's some bound electrons, the other saying there's different amounts, but the theories begin to diverge somewhere around in here. Okay, so what you want is an experiment that can test that. And once again, the short pulse platform sort of provides an avenue to try and do that as well. And the way that's done is we start with a similar thing where we take a material, which we say is higher Z material. We put we sandwich it between two lower Z material sandwich it with a lower Z material. We then use a long pulse laser to shock it, to compress it. When you shock something, you squeeze it, so the density then goes up. And then we use the short pulse laser to then heat it. And so we can do that in a systematic way where we can change the density of the material systematically and still maintain a high temperature. And then look at the emission. And the emission from this material that's in here gives us some idea, lets us know exactly how many electrons are still bound, because that emission is coming from bound electrons going from one orbital to another orbital. And we don't see the emission coming from those bound electrons. It tells us that the compression has pushed those electrons into the continuum. They're no longer bound states, they're continuum states. So that's kind of how that idea works and has worked, and it's worked really well. Okay, so I don't need that. Okay, so a little bit about electron ion of collaboration. This is something that we recently did using short pulse lasers in this same sort of platform. In all of those calculations, there's always a time scale for electrons and ions to come into equilibrium. And there's a formula, once again, there's a complicated formula, so ignore that, but just know that there is an expression that's used to determine how long it takes for the electrons and the ions to come into equilibrium. The problem is that there's been very little validation for that. So we don't really know how accurate it is. And what we found is that there are certain scenarios where if we change that value, we can match some of the time scales for fusion processes to take place, but we can change something else, something that's called mix, how long it takes materials to mix together. If we change that parameter, we can also have the same effect. So these things have not been experimentally validated. It's difficult to experimentally validate them. And so we propose trying to do an experiment to try and validate at least this portion, the electron ion of collaboration. Once again, this is a complicated expression, so ignore the expression. The key thing to know is that the time scale it takes for electrons and ions to equilibrate will affect what we call the line shape, a spectral line shape. And the spectral line shape is the emission as electrons go from one bound state to another bound state. And when that happens, you get the emission of a line, a spectral line. Well, the shape of that spectral line is dictated by, one of the things it's dictated by is how long the electrons and ions take to equilibrate. If the electrons and ions are in equilibration, there's a well-described formula for the width of that spectral feature. If the electrons and ions are not in equilibration, there is an expression for it, but it has a dependency on the difference between the electrons and the ions, the difference in their temperatures. And so we thought, well, you could utilize that using a short pulse laser platform, because when a short pulse laser, when you use a short pulse laser to heat a material, what happens is, once again, ignore a lot of this stuff and listen to what I'm saying. What happens is that the energy gets absorbed in the electrons. The electrons carry all the energy. So initially, everything is cold. The electrons are cold, the ions are cold. But when the laser hits hits a solid piece of material, the electrons get all the energy. And the electrons then transfer their energy to the ions. So if we could see a spectral feature during the time that the electrons are transferring their energy to the ions, we can look at the line shape temporally, look at the time dependence of that line shape, we can then, infer exactly how long it's taking the electrons to come into equilibrium with the ions. And the important thing to look here, this plot here is a plot showing the ion temperature starts cold. This is as a function of time. This is once again picoseconds, 10 to the minus 12 seconds. The ion, this is for a specific silicon line. Well, actually, I'm sorry. This is just for the material itself. The ion temperature starts cold. The electron temperature that we've deposited with the laser energy into is at 1300 electron volts. And you can see as time progresses, it takes about 35 picoseconds before the two come in equilibrium. So taking that information and then putting that into a calculation of what happens to a specific line feature, spectral feature, a specific transition between an electron from one charge state and one bound state to another bound state, you can see initially this line is really narrow and thin. But as time progresses, the line gets fatter and fatter and fatter as the electrons and the ions come in equilibrium. So what we proposed was try to make this measurement as a function of time and compare that to what the simulation would then, or that formula would predict how long it would take the electrons and ions to come in equilibrium. So we've done the experiment and the data is being analyzed now. This is kind of a complicated picture. Okay, let's just look at this for now. This is the hardware, what the hardware looks like, but just ignore that. We made this measurement, this time-resolved measurement of a line shape for 3 different cases: a solid material, 500 milligrams per cc, and then 95 milligrams per cc, and it's all done for silicon. And then we looked at a specific transition. So ignore this fuzzy stuff because that's from some other spectral features that, for the most part, we don't have to worry about. If you look at where the line is, these lines are drawn, you can see that this time is going this way. So time is increasing from right to left. The line starts kind of, in the solid case, the line starts kind of narrow, not super narrow, but kind of narrow. But then it starts to get fatter. And the time it takes for it to start to get fatter, the time it takes to reach its maximum fatness, if you like, that is the time it's taken for the electrons and ions to equilibrate. You can see then it starts to get narrower again. And that's actually from the entire target blowing down. So it eventually reaches equilibrium. The electrons and ions reach equilibrium, but when the entire target starts to blow down, the line begins to narrow. And that's because that line shape is dependent upon the density. So with the short pulse laser, you can heat it, as I pointed out before, you can heat it and it stays, it's pretty much solid density for a short duration, but then it blows down. And that line shape is also dependent upon that blowdown. So the idea is you can make this measurement just in here. So it's not very long, which is why we did it for different densities. So as you make the density lower, you can see it takes longer for it to reach its maximum width, and then you have the same experience, then it blows down. And the same thing here, it longer to reach its maximum width, and then it blows down. So we think the experiment worked and worked really well. It's a graduate student that is performing that experiment, and he's analyzing the data now to do the comparison to the calculations. Okay, I don't know how much time I have left.
We're at about 50 minutes.
I can't hear you, David.
Do you hear me?
Maybe I'll just look at my.
Okay, we're at about.
Okay, not much time. Okay, so I just looked at my clock. Okay, so I was going to explain this idea behind measuring thermal conductivity. This is another idea using the same idea of using short pulse lasers to isochorically, or what we call isochorically heat material, meaning you maintain a constant density and you heat it to a really high temperature. I'm not going to go into this because I want to leave some time for questions, and I want to get to this basic idea of trying to understand what Einstein's equivalence principle is, or whether it's true. So what is Einstein's equivalence principle? Einstein's equivalence principle is the idea that you cannot determine, you can't notice, or you can't see the difference between acceleration and gravity due to mass. Those things are basically the same. That's what Einstein's equivalence principle more or less says. And there's some complicated mathematics to go along with that, but ignoring all the math, it basically says an observer or someone in an accelerated frame can't tell whether or not that frame is accelerated from gravity that is due to mass, or if it's accelerated due to putting them in a rocket. You can't determine that difference. And it's a very fundamental premise. So the question is, can you test this idea? Other people have tested this idea in various forms and in various shades. And we thought, well, we may be able to test this using short pulse lasers. So how does this work? Okay, so if you look at a black hole, around a black hole is what's called the event horizon. And in vacuum, there's a constant creation and destruction of virtual particles. Okay, so you create a virtual particle, two virtual particles, and those two virtual particles then destroy. They're constantly doing that. At least that's what quantum chromodynamics would tell you. So at the edge of a black hole, if you create this pair of particles, virtual particles, one gets trapped into the black hole and the second one escapes into real life. So you then have a real source of emission. In this case, a boson, or you have a real source of energy which is escaped into the universe. So they don't destroy. And that process of creating this emission around the event horizon of a black hole is what's called Hawking radiation. If you believe that Einstein's equivalence principle is maintained, then you should have the same sort of process that occurs when a particle or a mass is accelerated. It creates the same thing, an event horizon, and that event horizon has the same process that occurs. It occurs where you're creating and destroying virtual particles right at the edge of the event horizon. And the same sort of thing will happen. You will have particles which you cannot keep up with. The one particle is on one side of the event horizon, the other particle is on the other side of the event horizon, which leads to a source of radiation, which is called Unruh radiation. Three guys developed the theory for this. And I think the third guy got his name attached to it, which is Unruh, but it's called Unruh radiation. Well, it's controversial as to whether or not it's ever been seen before, but the requirement for an accelerated mass to generate the event horizon, and hence Unruh radiation, is a potential mechanism for using a short pulse laser to do this thing. You say, how? Well, with a short pulse laser, you interact with a solid material, and I think this is the last few graphs. You accelerate particles by two processes. One is called target normal sheath acceleration, and those particles get accelerated to tens of MeV, really high energies, tens of MeV. And with a thin enough target, you can generate a process called breakout afterburner acceleration, which is taking a really thin target, and you essentially accelerate the entire focal spot of material in one blast. And both processes have been observed already. The second one, particles can reach much higher energies, approaching almost 100 MeV. And so what a group of us have been looking at is, well, if that happens, since you're starting from something that's stationary and being accelerated, you do generate this event horizon, and hence you would expect Unruh radiation. And the question is, with the bound states, if you accelerate a material which to a high enough acceleration, and you end up with bound states, the question is, how does that unirradiation then perturb those bound states when those bound transitions take place? And when they do perturb them, will you see the signature of the unirradiation? And the calculations for the unirradiation of these scenarios is pretty big. It's as high as in some cases, as high as a kilovolt. So we're sort of in the process of designing an experiment that will try to look for the effect of unirradiation on bound states and accelerated ions. Okay, so that's it. To summarize, I didn't talk about the thermal conductivity part because I was worried about running out of time, but we can use these short pulse lasers to study matter at conditions that are comparable to stellar interiors, and we're in the process of doing that. Some of these things have already been published. Other things are in the process of being published, and some experiments are ongoing. Thank you, and I hope we can encourage some more young scientists to come and join the field.
Okay, thank you very much, Ronnie, for
Do I stop sharing?
Sure. Yeah, we'll see if somebody wants to ask a question that involves seeing your slides.
I can't. I think you're muted.
I can hear you.
Maybe.
Okay, maybe that's just on
I don't know who muted. I didn't mute you.
Maybe that's just on your side.
But we can't hear you, David.
Okay. Well, to everyone else who hopefully can hear me, feel free to put questions into the Q&A.
I can't hear you.
Questions.
Wait a minute.
Can you hear me, Ronnie? Or
feel free to ask some questions. Is it just me, or I can't hear anyone?
I think it's
just me. Oh shoot!
Okay.
Could you guys hear me?
Yes,
you can hear me fine. Okay. I don't know. Oh wait a minute. Hang on. Maybe this is why.
Can you hear me now?
Yeah, I can hear you now.
Okay, that's good. We've got two-way communication again.
Sorry.
Do we have any questions from the audience?
Looks like there's something in the chat.
Well, I think we were just discussing the question of who can hear whom. Yeah.
Okay.
Any questions from the panelists?
Always makes me nervous when there are no questions, because that means.
Good. Nope, we have a question.
Okay.
All right. Maybe there was something that was held back. Suddenly we got a bunch of them that are coming in. So Wen Chin asks, the shape of lines are characterizing energy range. Actually not. Let's see. Can I? Not quite sure what you mean, Wen Chin. Maybe can you type in the chat what you are asking, or maybe ask a more full question. Let's see, can we go to, so next question, Mehdi asks, can you tell us a bit more about continuum lowering of solids?
Yeah, so continuum lowering is often called also pressure ionization, and it's from ions, as you push them closer and closer together, those outer orbitals begin to overlap with one another. The positive charge from ion 1 begins to affect the bound states of ion 2, the outer bound states. And that's typically what's called continuum lowering. And it happens in solids without any added pressure. You effectively have continuum, you create continuum states, which it's the conduction band. So you form band structure in solids when that happens. But when you're in this condition where you have ions that are also moving, they're not static, it's difficult to produce the actual band structure, because the ions aren't actually static. They're moving around.
Okay.
I hope that answers your question.
Yeah, I think so. Sound good. Let's see. Julie asks, how did you go from nuclear engineering to studying stars and plasma?
Oh, okay. So at Michigan, it's an interesting situation because I was studying plasma physics, and depending upon the university you go to, that department can be in anything from electrical engineering, mechanical engineering, astrophysics. You know, Princeton's in the astrophysics department. It's sort of a stepchild. Many physics departments don't consider it physics, so they won't put it in the physics department. So nuclear engineering was the department that did plasma physics at Michigan. That's how I ended up. I mean, I really didn't go from nuclear engineering to plasma. I was always studying plasma physics. It was just in the nuclear engineering department.
Cool. Okay, thanks. Let's see. Liam asks, do your experiments validate any of the CL/IDP models?
Continued lowering or, oh, okay. So
potential depression.
Did they validate it? Oh, that's Liam. So our best agreement comes from comparison to Stuart Pyatt. So Stuart Pyatt is the best agreement, but even Stuart Pyatt begins to break down as we go to higher densities. So the experiment that we did, we did it on aluminum, and we started at 3 grams per cc, 2.7 grams per cc. We tamped the material, we tamped the target with diamond, which starts at 3 grams per cc. So because the tamp was higher in density than the tamped material, when we heated it, it isochorically heats. And so initially it just squished it. So it pushes it up. But then we did the systematic thing of compressing it with the laser, with the long pulse laser. And we eventually got it as high as 12 grams per cc. Stuart Pyatt agreed up to about just over 7 grams per cc. And then Stuart Pyatt didn't agree anymore. So I would not really call Stuart Pyatt, I mean, most of my friends that are theoreticians get mad at us when we call those models, because they're like, well, those are really ad hoc. They just have a hard boundary as to the difference between the continuum and the bound states. And they would tell you the right answer is purgatorial, which systematically allows those bounds, the bound electrons, the wave functions to delocalize in a systematic way. So even when they push them into the continuum, the wave functions aren't fully delocalized. They still have some characteristics which associates them with a given atom. So that's kind of a long answer. But the bottom line is that the best agreement we have to date is Stuart Pyatt.
Okay, great. Thanks. Let's see. Kevin asks, a great presentation. I might have missed it, but why was the laser wavelength changed from red to blue as it entered the chamber?
No, you didn't miss it. I didn't talk about it because it's a rabbit hole that I don't want to go down. When lasers interact with matter, I'm going to tell a little bit of a story. In the early days, people thought with 100 joules, you would make fusion with laser, taking lasers and directly hitting targets. What they found was that when you take the laser and hit the target, they didn't get all the laser energy in to the target. And initially they were confused. They made a bunch of measurements and they found out the laser drives these instabilities in the plasmas. They're called stimulated Raman scattering and stimulated Brillouin scattering. The laser drives those instabilities. The wavelength of the light couples to the plasma frequency, which oscillates and creates a scattered wave back at a slightly different frequency. But the bottom line is that it doesn't heat the electrons. So what they with a lot of experiments, what they discovered was making the wavelength shorter and shorter and shorter, the coupling became better and better and better. So that those instabilities are dependent upon the wavelength of the laser light. Now you may say, well, okay, what? That's actually the reason why the implosions aren't driven directly by the laser. They're actually driven by X-rays. So you heat the walls of this holorum, the gold, and the gold generates X-rays, and the X-rays are actually what heats the capsule. And that's because you want the shortest wavelength possible to heat the capsule material, because you couple the energy more efficiently. So that's really the reason why, is you convert the red to blue, because even in heating the walls to make the X-rays, that coupling efficiency is a lot better in blue versus red.
Thanks. Okay, why don't we take one last question here. Bree asks, how often do you work with theorists to do numerical simulations so that you can compare your experimental results with the theoretical expectations?
They're an integral part. I mean, we work as a group. So for my particular case, when I have an idea for an experiment to test something, I form a group with theory people and modeling people, and I try to recruit them to a crazy idea. and if it works, we get a team and we then work hand in hand. So it's not me going off and doing an experiment and then afterwards conversing with them to see if they like it or they agree. In the inception of the idea of potentially we could test this using this idea, there's a group of us discussing the idea and whether or not this is a good way of testing it. So I would say I work hand in hand with them constantly. There isn't a barrier. There's an open discussion. And it just so happens that I do my best work in a laboratory and they do their best work on a computer, but we don't see each other as, in boxes.
Great. Okay, why don't we wrap up our Q&A at this point. So let's thank Ronnie again for a very interesting talk and giving us some insight into his work and things at Lawrence Livermore. So at this point, any students who would like to continue to just chat informally with Ronnie and talk about his path in science or anything else you'd like to discuss, you're welcome to stay on here. Otherwise, we can stop the recording, Finn, and we can promote to